how you can, how from a signal flow graph, we started on the topic of how you can derive the transfer function of a system based on the signal flow graph. So just a brief, so let's do an example and then it becomes, so this was the formula for Mason's gain formula. So here what we are interested, like from a signal flow graph, what we need to do is we need to find separate, like we need to find what all are the forward paths present in the signal flow graph, then what are the total loop gains and all, and depending on all those values, then finally you can combine them together, and using this formula where T is equals to 1 by delta summation of Pk into delta K, using this formula you can find out what is the overall transfer function of the system. So we started off with this example. So this is a signal flow graph, let's say, which was provided to you. And so the first step for applying this Mason's gain formula is to find out how many forward paths are present. So here you see that there were two forward paths. So one was starting from Y1, Y2, Y3, Y4, Y5, Y6. Then the other one was Y1, Y2, Y3 directly to Y5 and then Y6. So we had two forward paths. So once you have identified the forward paths, the next step is to write what are the corresponding forward path gains. So okay, so this is one forward path gain, this is the second forward path gain. Okay, so this is step number 2. In the third step, what you need to do is that you have to find out how many loops are present in the graph. Okay, so here we saw that there are 5 loops. So this is one loop. This one is so this is loop number 1, you can say. This is second loop. This is a small third loop. The outer loop is a fourth loop, and this whole thing combined together starting from Y3 through G, Y5 and then through H to Y3 again. This will consist of, let's say, loop number 5. So now that you know how many loops are there, you can write what are the corresponding loop gains. So these are the corresponding loop gains for each of these loops. Fine. So then what you need to do is that we will find out that how many non-touching loops are present in the system. So first of all, we will find how many two non-touching loops are present. So what do I mean by two non-touching loops? Here you see that out of these 5 loops that you have in the signal flow graph, so this loop number 1 and loop number 2, these two are not touching each other. So this will comprise of one pair of two non-touching loops, right? And so first of all, there are like 3 loops which can, so that will be one pair of two non-touching loops, and then another pair of two non-touching loops will be this loop number 1 and this loop number 3. So these two are also not touching each other. So this is another pair of non-touching loops. But if you consider all the other loops like loop number 4 and 5, you see that loop number 4 is touching all the other loops. Similarly, loop number 5 is also touching all the other loops. So that means they will not be considered as non-touching loops. So here you see that there are 2 non-touching loops. So number of non-touching loops is 2. And then now let's say that in this case, if you had like another loop somewhere over here after Y6, then what you can say is that there might be a pair of 3 non-touching loops also. So if, let's say, for example, that is not in this signal flow graphs, let's say you have another loop somewhere over here. This is actually not here, but just for the sake. So if there was another loop over here, so then you can see that you can have like a pair of 3 non-touching loops also. So this loop number 1, loop number 2, and this loop, this will comprise of 3 loops which are not touching each other. Similarly, loop number 1, 3, and this loop, these are also not touching each other. So that means here, if there was another loop, so you will have a set or a number of 2 non-touching loops and a number of 3 non-touching loops also. But this is actually not here in this signal flow graph. This is not here, so we'll not consider that. So then we found out what is the number of 2 non-touching loops. So that is 2. So then what you will do is that you will find what are the pairs of non-touching loops, of 2 non-touching loops. So the first pair will be Y2, Y3, Y2, and and this is y5, y5. This will be one pair of non-touching loop, and the gain of the gain product of this first non-touching loop pair will be given by B F into J. Similarly, for the second, you write what is the second non-touching loop pair. So the second non-touching loop pair will be y2, y3, y2, and y4, y5, y4. So this will, and the gain of this will be equals to B J D into I. Right? So then what we'll do is that once we have found out, so here, since there are no three non-touching loops, so we don't need to go to the next step. If there were like three non-touching loops, then what you have to find out is that again you have to find out what is the product of gain product of the number of pairs of three non-touching loops which are there. So once you have found out all these, then what we'll do is that we'll find what is the value of the determinant delta. Here you see that the value of delta is given by 1 minus sum of all the loop gains of individual loops. So we have found out the loops, the gains of individual loops, that is this step is done. Then we have found out that sum of the gain products of all possible combinations of two non-touching loops. So in this signal flow graph, which we are talking about right now, there are only two combinations of two non-touching loops. So we have found out what will be the sum of the gain products of those two non-touching loops. Then if you had three non-touching loops, then you have to go for the third or rather the fourth term also. So on and so forth, you will have to keep on adding depending on how your signal flow graph looks like. Right? So then we'll find out what is the value of delta. Okay. So here delta will be given by, so it will be 1 minus individual loop gains. So if you write all the individual loop gains, so the loop gains are Bj plus Gh plus Cdh plus Di plus F, plus you will have the addition of sum of gain products of all possible combinations of two non-touching loops. So the two non-touching loops were BFG and BJDI. So this will be BFG plus BFJ plus BJDI. Okay, so the value of delta we have found out. Then what we need to do is that we will see what is the so then what in the Mason's gain formula we have seen that the value of T is equals to 1 by delta summation over K Pk into delta K. Right? So here, so now what we need to find is the value of delta K. So delta K basically, so let's say that for the first forward path, if you consider the first forward path, you see that none of the loops, so all the loops that are present in this signal flow graph, it touches the first forward path. Correct? So so there is no loop which is not touching the first forward path. So in that case, the value of delta 1 will be equals to 1. Similarly, if you see the second forward path, which is going in this way. So in the second path also, there is no loop that is not touching, that is non-touching to the second forward path. So in that case, the value of delta 2 will also be equals to 0. So we know the value of delta 1 and delta 2. So then what we'll do is that we'll find the summation of this Pk. So this value of Pk is basically the gain, the path gain for the kth forward path. So you know that, so you will write the value of 1. So delta will come in the denominator. Delta is nothing but this term Bj plus Gh plus Di plus F plus and in the numerator you will have the value of forward path gain. What is the value of forward path gain? So this was the first forward path. So ABCDE multiplied by 1 plus ABGE multiplied by 1. So this will give you the final transfer function of the overall system. Like this y6 by y1 will be, so this is y6 by y1 will give you this transfer function. So here you see that using this Mason's gain formula, what we can do is that first of all, we don't have to, you just have to find out simple steps, and combining those using this formula you can find out the transfer function of the system very easily. So here you don't have to, in case of a block diagram, if you had to do multiple steps while reduction of the block diagram in order to find out what is the overall transfer function of the system. So you can substitute that complex or complicated or tedious block diagram reduction technique by simply using this Mason's gain formula, which is which will also give you what is the overall gain or the ratio of the output to the input of your system. Similarly, let's try to do another example, and so that it will be a little bit more clear to you. So here also you see that there are the number of forward paths in this signal flow graph are like the value of n is equals to 2. So forward path number 1 is starts from x1, x2, x3, x4, x5. Okay, and then forward path number 2 is x1. Yeah, so forward path number 2 will be equals to x1, x2, x3. So from x3 you will move directly to x5. Okay, so this is like x1, x2, x3, x4, x5, and then x1, x2, x3, and then you move along this one and you reach x5. Okay, so then, and now the number of, so if you write the forward path gain, so this will be P1. So the value of P1 will be equals to A12, and yeah, so the value of P1 will be equals to A12, A23, A34, and A45, and P2 will be equals to A12, A23, then A35, right? So then, so this is the first step that is done. Then we'll find what are the number of individual loops which are present in the system. So what is the number of loops that are present in the system? So this is one loop, one, then you have two, then this is another loop, three, then you have four over here, you have five over here, and then you have six over here. Did I miss out anything? So let's write the loops. So there will be, so one loop will be x2, x3, x2, then there is x2, x4, x5, sorry. So another one is x4 to x4. Then you have x2, x3, x4, coming back to x2. Then you have x2, x3, x5, coming back to x2. And what else? This is also there, no? x3, x4, x5 to x3. x3, x4. No, this is not coming back here. This is not a forward path. Did I miss out any loop? One. This one is another loop. x2, x3, x5. No, this I have already written. So there are like 4 loops. Correct? So once you have found out the loops, so what you need to do is that now you can easily write what are the corresponding loop gains, the gains for this corresponding loops. And once you have, so what we'll do is that the representation what we'll do is that for the first loop the gain will write as P11. For the second loop we'll write it as P21, and so on and so forth. So if there are 4 loops, so there will be P31 and P41. Okay, so the second, as we have already seen that the second term of this of the loop of the subscript, that will actually denote what is the number of loops that we are considering. So here we are considering individual loops, so that will be, so that means the second term will be 1 and the first term will be the number of so the first loop, the second loop and the third loop, so the numeric value. So P11, P21, P31, P41. Similarly, what you will do is that you will find out how many number of non-touching, 2 non-touching loops are there. So there is one loop, so this loop and this loop are not touching with each other. And similarly, this loop and this loop are not touching with each other. So here also you will have two combinations of non-touching loops, and you can find what is the corresponding. So once you have found out this, so what you will do next step is that you will find out what is the loop, what is the loop total loop gain. So loop gain means, so this will be equal to the gain product of the two of the pairs of non-touching loops. So if you have two pairs of two non-touching loops, so you will find the values of P11 and P22. Now if there are some combinations of 3 non-touching loops, then you will find out what is the value of in case of that, you will find out what is the value of P13, then P23, depending on how many 3 non-touching loops are there. So once you have found out all these values of P1, P2, P11, P12, P13 and all, then you will find the value of delta, which will be given by 1 minus, so summation of, so it will give you a summation of P, suppose N1, plus you will have summation of K, P of K2 minus summation of, let's say over J, P of J3, and so on and so forth, depending on how many non-touching loops are there. So once you have found out this value of delta, then what you will do is that we need to find what is the value of delta K. So delta K is nothing but the, so we'll consider the first non-touching first forward path, and we'll see that, so here you see that for the value of, so for the first forward path, which is this one, see all the loops are touching the first forward path. So that means the value of delta 1 will be equals to 1. But when you consider the second forward path, the second forward path moves like x1, x2, x3 goes to x5 directly. Now you see that there is this loop, this A44, this loop is basically not touching this forward path. So that means the value of delta 2 will be equals to 1 minus A of 44. So that means what we will do, so the value of delta will be given by 1 minus the gain of the loops which are not touching that corresponding forward path. So once you have found out this value of delta 1 and delta 2, you know P1 and P2. So then you can write, so this will be equals to 1 by delta 1, P1 delta 1 plus P2 delta 2. So this will give you the overall transfer function or the overall gain of your system. So this concept of Mason's gain formula, this is clear to you? Like how to find out, how to apply this Mason's gain formula and find out the transfer function? Is the Mason's gain formula clear to you?
Yes.
Yes. Okay. Okay. Fine. So there are a few, I have given a few practice problems. You can try to solve this signal flow graphs and find the what is the transfer function of the system. So this is for just for your practice, and you try to do it, and then you see whether you are facing any difficulty while calculating the overall transfer function of the system or not. So these are a few practice problems. I think these you can do at home. So then comes the application. So till now we have seen that you have been given with, so if you have a set of algebraic equations, from those algebraic equations you can draw the signal flow graph, and once you have drawn the signal flow graph, you can find what is the overall gain of the system. Okay, so now so this signal flow graph or this gain formula, it can be applied to a block diagram also. Okay, so this Mason's gain formula, it can be used to derive the transfer function from a block diagram. So what are the steps for doing that? So first of all, what you need to do is that you have to draw the signal flow graph from the block diagram. And once you have drawn the signal flow graph, from there you can apply the Mason's gain formula. Now, how to draw so now if you are given with a block diagram, how do you draw the signal flow graph from the block diagram? So there are a few steps for that. First of all, in a block diagram, you represent each summing point, each takeoff point, and if there is any variable between two nodes or between two blocks, you represent that as a node. Okay, so the first step is to denote or is to represent the nodes or identify the nodes in the block diagram. Okay, so which one will correspond to as a node? Like, if there is a summing point, that will become a node. If there is a takeoff point, that will also considered as a node. If there is a point which is lying between two blocks, that will also be considered as a node. So once you have identified the nodes in the system, then in the block diagram, then what you do is that then you draw the interconnections between the nodes according to the block diagram. And if there is a negative feedback path, then you represent the gain for that corresponding branch with a negative sign, and then you join the branches together according to the block diagram, and that will give you the overall block diagram signal flow graph from the block diagram. So now let's say that if this type of a block diagram is given to you, so then first of all so the first thing is that you identify what is the input node and what is the output node. So the input node here is Rs and the output node here is Ys. So what we want is that we want to find what is the value of Ys by Rs. Okay, so this is our end goal, you can say. So for that, what we will do is that we will So there are multiple ways of finding the overall transfer function. You can do block diagram reduction from this block diagram, or what you can do is that we can draw the signal flow graph, and from there we can easily find out what is the value of the transfer function. Okay, so here there are multiple so you see that all the summing points, so there are 1, 2, 3, 4 summing points. So each summing point will correspond to one node. There are takeoff points. There is one takeoff point over here, one takeoff point over here, 3, 4. There are 4 takeoff points. So these 4 takeoff points will also be considered as 4 nodes. And you see that between this block G1 and G2, there is a branch or there is a path between the block G1 and G2. So the signal at this point, that will be also considered as a node Y3, let's say. And and we have in this forward path, we have actually covered all the points which are there. So you end up with like total of 8 nodes total of 9 nodes other than the input and the output nodes. So if you just draw you write, so Rs is your input, Ys is your output. Apart from that, you just draw the 9 nodes, so Y1 to Y9. So once you have denoted that, then what you do is that here you see that between Y2 and Y3, there is a gain G1 connected. So this between Y2 and Y3, you will have, this branch will have a gain of G1. Similarly, between Y3 and Y4, there is G2. So this branch will have a gain of G2. Then there is a feedback path connecting between Y3 and Y2. So between Y4 and Y2. So between Y4 and Y2, there will be a negative feedback path. That's why it is denoted by a minus sign. So minus H1. Then again, if you come here, you see that between Y6 and Y7, there is G3 and there is G4. So you have G3 over here, you have another branch, which is another path, which is the gain of which is given by G4. And similarly for H3, so H3 is connected between Y9 and Y5. So here between Y9 and Y5, there is H3, which is coming in as a negative feedback. So that means it will be denoted by minus H3. Similarly, you connect H2 between and here H2, you see that it is going in the positive terminal. So that means this is a positive feedback loop. So this will be denoted only by plus sign. So between Y8 and Y1, you have H2. So now you have, so this is the overall signal flow graph, which representation of this block diagram. So once you have found out this signal flow graph, now what you can do is that you can apply that Mason's gain formula and find out what is the overall gain of the system, or overall gain of the system means what is the ratio of the output to the input. So here, since the gains are given in terms of transfer functions, so that means what you will end up with after applying this Mason's gain formula, what you will end up is you will find out what is the transfer function of this Ys by Rs. Fine. So this is so here in this, so let's say that this is another block diagram which is given. So this summing point, this is, let's say Y1, this is Y2, this will consider as another Y3, and this is a takeoff point. So this will be, let's say, Y4. And Rs and Cs, these are your input terminals. So if you draw the signal flow graph, so you have Rs over here and you have Cs over here. Then you have Y1, Y2, Y3 and Y4, right? So these are all so connected like this. So between Rs and Y1, basically there is no gain involved, so this is unity gain. Between Y2 and Y1 and Y2 also, this is unity gain. Between Y2 and Y3, there is a gain of G1. Between Y3 and Y4, you have a gain of G2. And between Y4 and C1, you have a gain of 1. Now this H2 is connected between Y4 and Y3. So between Y4 and Y3, you have, and this is connected in the negative feedback, so you will have minus of H2. Again, between Y4 and Y2, you have H3, which is again going in as a minus. So you will have between Y4 and Y2, you will have minus H3. And this H2 is connected between Y3 and Y1. So between Y3 and Y1, you will have minus of H1. So this is your overall signal flow graph from this block diagram. So once you have found out this signal flow graph, then you can easily apply that Mason's gain formula, and after applying that Mason's gain formula, you will get the value of Cs by Rs. So Cs by Rs is basically the transfer function of the overall system. Okay, so this is how you draw the signal flow graph, or you can derive the signal flow graph from a block diagram. And similarly, there are some more examples. You can try this practice at your home. Like you find out what is the, or you draw the signal flow graph, and then you try to find out what is the value of the transfer function. Also, what you can do is that you can try to do block diagram reduction and then compare whether you are getting the same value, because at the end of the day, the transfer function of the system remains the same, irrespective of how I am deriving that transfer function. So you draw the signal flow graph and find the transfer function from that, from that by using Mason's gain formula. And then in the next step, what you do is that you do block diagram reduction, and from block diagram reduction also you try to find out what is the value of the transfer function of the system, and you see whether the two systems or the two results are matching or not. Ideally it should match. If it's not matching, so that means there has been some mistake in either of the two calculations. So these are some examples. So with this, we will. So the module 2 of the syllabus is actually over with this. So next, what we'll do is that we'll move on to the module 3, which deals with the time domain analysis of a control system. So till now, what we have done is that we have seen that how you can model a system, how you can represent a system in different forms. You can represent a system in form of a transfer function, in form of a block diagram, a signal flow graph, and how to come with the how to derive those kind of systems. Okay, so now we know what is there inside the control system. So the second step is that to find out that how that control system is actually behaving. So how the control system is behaving, it means that it will, so either we'll see that if, so each in a control system there will be an input, there is an output. So now the relation between the input and the output, that relation can be studied in different domains, like in time domain, in frequency domain. So now first of all we'll study what is the time domain performance of a control system. So basically this time domain analysis, it refers to the analysis of the system performance in time. So obviously the name time domain means that we will be analyzing the performance of the control system for a particular input in the time domain. So that means that how the output of that control system that is actually changing with time, or how it is varying with time, that is that will be studied while we are doing the time domain analysis. So this for the time domain analysis, there are like two kinds of responses which we usually study. So one is natural and forced response. The other one is transient and steady state response. So the overall or the complete response of the system is given by a combination of both the responses. So that means if you know the natural and the forced response, so the combination of those two, and the transient and the steady state response. So the combination of the transient and the steady state response combined together will give you the overall time domain response of the system. Okay, so if you see the, so by if you see the definition of transient of natural response. So natural response basically means that the response of the system with only initial conditions present and with all the external forces set to 0. So that means if you have a system, so for example, if you have let's say you have a series RLC circuit and there is no driving voltage or current source. So you just have a, so you have an R and L and a C. You have a circuit like this. So this circuit, so this is R, L and C. And this circuit has been subjected to some initial condition. So some initial condition means there is some energy which is stored in this inductor as well as the capacitor. But in this circuit, there is no external voltage source or current source which is driving the circuit. So if that is the kind of configuration of your circuit, so then the response that you are getting, the output, so let's say if you are trying to see the output against this capacitor. So if you want to see what is the voltage, how the voltage is varying across this capacitor, then this will be known as the natural response. So natural response is, in other words, you can say that this is equivalent to a zero input response. Zero input response means that only the decay or change in the output signal because of whatever is the initial condition present in the system, that is known as the natural response. And the forced response, it means that if you have the if the system has a zero initial condition and the system is subjected to external forces for an electrical circuit, the external forces will be some current source or voltage source would be there. So if you have an RLC circuit, let's say, which has zero initial condition, but which is being driven by an independent voltage or a current source. In that case, the response of the system, that will be known as the forced response. Now coming to the definition of transient response. So transient, as the term, this transient means something which is temporary, right? So that means that the part of the time response which is actually the part of the time response that goes to zero, or which decays down to zero as you increase the amount of time. So as time becomes large, or as time goes to infinity, the part of the time response that goes to zero, that is known as the transient response. And the transient response is basically, it can be generated whenever there is, it is generally generated whenever there is any change in the input from the equilibrium position. Let's say your equilibrium position means that it is sort of fixed, or it is maintaining a fixed position. So now if, let's say that if there is suddenly there is any change in that equilibrium position, you are providing a sudden change in the input. So if you provide a sudden change in the input, what will happen? The system will deviate from its equilibrium state, and it will go to, it will move somewhere else. So that means that the transient response is basically generated whenever there is any change in the system condition from its equilibrium position. And this change can be because of some change in input. It can be because of some external disturbance which is there, some kind of switching mechanism which is there. Because of that, whenever the system is moving away, or it is deviating from its equilibrium state, the nature or the dynamics of the system, of the output which is following during the initial stage after applying that change in the input, that will be considered as the transient response. And the transient response will, the part of, so the transient response, the properties of transient response is that as time becomes infinity, the value of this transient response becomes equals to zero. So you can write mathematically that the limit t tends to infinity if transient response is given by C TR of t, so this will be equals to 0. Okay, so now let's say that if you have a pendulum, okay, if you take an example of a simple pendulum, and that simple pendulum is present in a equilibrium position. So this is, let's say, a simple pendulum, and this is the equilibrium position that you have. Now if I disturb this system slightly, if I give some let's say if I provide some kind of force to this system, so what will happen, that it will try to move. So now it will no longer be in its equilibrium state. It will move somewhere here. Then again it will keep on sort of oscillating until and unless it again goes back to its original equilibrium state. So this path that it follows, or the nature or the dynamics that this pendulum follows, once an input or a change is provided to the system, that is basically known as the transient response. And the steady state response means that after the transients in the output has died down, so after that whatever response, the value of the response is present in the system, that is known as the steady state response. So the part of the time response of the system which is present after the transients have died down, and this is actually a fixed value as time goes to infinity, that is known as the steady state response of a system. Now for studying the so in order to analyze the steady state or the transient and steady state behavior of a system, so the first step is that we need to obtain the mathematical model of the system. We have to, so once you have known the mathematical model of the system, so if you remember that what was the main purpose of doing a modeling. So the purpose of doing modeling was that whether we can represent the system in a simplistic way, or in a way such that we can determine what will be the output of that system for a fixed set of input. Now, in general, when you are dealing with a practical control system, so the inputs to a practical control system, that is always not known to us. Okay, so before designing a control system, you don't know what kind of inputs will be provided to your system. So the inputs, they can vary randomly with time. So for example, if you have a radar tracking system, so then the position, and so you have your system design, but the position and the speed of the target which needs to be tracked by the radar, that is not in your hand. That can vary in a very unpredictable manner, and obviously it is not always possible to express that in a deterministic way. So for that, what we need to do is that we have to design the control system in such a way that it will, so ideally it is, so that means ideally it is difficult to design a control system which will perform satisfactorily to any kind of inputs which is provided. That is not practically feasible. So at best, what we can do is that we can design a system and we can see, or we can evaluate the system performance with respect to a fixed set of standard test signals. Okay, so the standard test signals, basically they so there are multiple test signals which are generally used to evaluate the performance of a control system. So these test signals which are generally used are, one is impulse. Then you have a step signal you can use. So step signal basically denotes if there is a sudden change in input. So the step signal is equivalent to that. Then a ramp signal. So ramp means if there is a constant change, or if there is constant velocity change, that kind of an input will be represented by a ramp input. Then you can have a parabolic input. So parabolic input basically represents a constant acceleration state. And then you have sinusoidal. So sinusoidal basically that is generally used for studying the frequency domain analysis. So for now we will be mostly concentrating on the impulse, step, ramp and parabolic, these four kind of responses to a control system. So basically, so why do we choose why do we choose step, impulse, ramp and parabolic and not anything else? So if you see that the characteristics of the actual signals, so mostly whenever there is a control system present, so if you have the properties or the output of the control system, they are generally severely affected if the system is being provided with a sudden shock, or there is a sudden change in the input. So those kind of inputs, they can be represented easily using this impulse. So impulse, if there is a sudden shock or a sudden change in the output, there is a spike in the input, so that will be represented by an impulse signal. So if you have a sudden change in the input signal, and that sudden change is actually getting prolonged for a long time, so that will be represented, that kind of the effect of that kind of signal on the output, that can be represented if we study the system, if we study the performance of the system using a step input. So that's how we have actually selected. So there are these four kind of standard test signals: impulse, step, ramp and parabolic. These four kind of signals are usually used for studying the time response characteristics of a system. Okay, so now let's see that so a unit impulse signal. So basically an impulse means it will have a non-zero value at impulse means that the signal will have a value of 0 at all times other than at t equals to 0. If you write the mathematical expression for this impulse signal, so delta t will be equals to 0 for all values of t which is not equals to 0. And if you integrate the value, integrate this impulse signal with respect to time from -infinity to +infinity, it integrates to 1. And if you do the Laplace transform of this unit impulse, so the Laplace transform of the unit impulse is equals to 1. Now if you see the unit step signal, so unit step signal means the signal switches to 1 at a particular time instant and it stays at that position indefinitely. So that means ut will be equals to 1 for all values of t greater than equals to 0, and ut will be equals to 0 for all values of t less than 0. and the Laplace transform of this unit step signal is equals to 1 by s. Then we have this ramp signal. So ramp signal, basically it increases linearly with time. So that means if you write mathematically, the value of RT will be given by A into T. So this value of A so it will be RT will be equals to AT for T greater than equals to 0, and for T less than 0, the value of RT will be equals to 0. Similarly, the Laplace transform is given by A by S square. Again, for a parabolic signal, the expression goes like that: for T greater than equals to 0, xt will follow an equation xt equals to a t square by 2. And the Laplace transform is given by a by s cube. Okay, so now this test, so these are like the 4 standard test signals which are generally used. So the standard test signals are simple to like you have seen that the mathematical expression of these standard test signals are quite simple. The corresponding Laplace transform is also quite simple. And if you observe something is that as you move from step to if you see that from step to ramp to parabolic, what you will see is that the change in signal becomes progressively slower with time. So in a step signal, there is an instantaneous jump in the amplitude. So using a step signal, what we can do is that we can find out what is the system's how the system is able to respond quickly, how quickly the system is able to respond to a change in the to a sudden change in input. So this step signal, and then for ramp signals, what we can do using ramp signal is that we can test the system's ability to respond to an input that is varying linearly with time. Similarly, for parabolic, so the variation is 1 degree faster than the ramp signal. So if you see the mathematical expression, you see that if you take a derivative of this parabolic signal, you will get this ramp. Another derivative of this ramp signal will give you the step response, and another derivative will give you the impulse. So these 4 test signals, they are basically related to each other by a simple mathematical operation. So either once you are moving from step to parabolic response, so you'll have to do one level of integration one after another, and if you are moving from parabolic to impulse, you will have to do one or the other order of derivative. This is very important because later on you will see that if you can find out what is the response for one kind of a signal, then it becomes easier to find what is the response for the other types of signal without going through the whole process. So now let's see what is the first order system. So in a first order system, so basically first order system means the number of poles in the system is 1. Okay, so the denominator will have the power of s in the denominator. The maximum power of s in the denominator will be equals to 1. So let's say that you have a first order system whose transfer function is given by 1 by st. Okay, so if you make a control system or a control loop out of it, and if you have a unity feedback, so then the overall transfer function of the system becomes 1 by 1 plus ts. Now this t basically, this t is basically a constant, and this is known as the system time constant. And what is the significance of this system time constant? The value of t, it characterizes the speed of the response of the system. So if you are providing so if you have your response, your input provided to the system is rs. So how quickly the system will be able to respond to this value of rs, that is being characterized by the value of t. So if you have a higher time constant, so it implies that the system will slowly respond to the input. Now if you have a lower time constant means the system will be very fast acting, and it will respond very fast to the input that you have provided. So all these first order systems, they will have the same output in response for the same input that you are providing. Okay, So now let's see what will be the type of response for this standard first order system. So for this first order system, let's say if you are taking this unit impulse, so unit impulse means the value of Rs will be equals to 1. So you can write that the output expression, so Cs will be equals to, so we know that for this, so Cs by Rs for this first order system is 1 by 1 plus Ts. Right, so this is the transfer function of the overall system. So Cs will be 1 by Ts multiplied by Rs, and Rs here is equals to 1. So if you do the Laplace inverse of this term, so it will give you that Ct, the value of Ct will be equals to 1 by T e to the power minus T by tau. If you draw this response, you will see that it is an exponentially decaying signal. Now you see that exponentially decaying signal, this term, this e to the power minus T by tau, as T tends to infinity, the value of this part becomes equals to 0. So e to the power minus, so as T tends to infinity, the value of e to the power minus T by T, this tends to 0. So that means this part will basically comprise of the transient part of the overall so this is the overall response or the overall time response. This is basically the overall time response of the system towards a impulse input. And you see that here this e to the power minus T by tau, this term basically is the transient response, because this term actually is going down to 0 as T tends to infinity. So the transient part of the response will be given by 1 by T e to the power minus T by capital T. And here the steady state response is equals to 0. So this two, the CTR plus CSS will give you the overall response of the system. Okay, so I think it's almost, we have come to the end of the class. So in the next class, what we'll do is that we'll study the response, or we'll see what is the time response for when the first order system is provided with or is excited with a step input or a ramp or a parabolic. So for this, actually, what you have to go through or brush up your concepts of Laplace transform and inverse Laplace transform. So it would be better if you can just revise. If you remember, then it's well and very good. But in case you have, if you have forgotten about this Laplace transforms and the inverse Laplace transform, it will be good if you can revise that, because in this time domain analysis, we'll be dealing a lot with this Laplace and inverse Laplace transform of a signal. Okay, so is there any doubt till now?
No, ma'am.
Okay, so what I would suggest is that you can try the practice problems that I have already given. In case you are facing any difficulty, we can you can ask me. We'll try to clear that up in the next class, and then again tomorrow we'll continue with our discussion on this time response, time domain analysis of control systems. So if there are no more doubts, then we can end the class here today. Thank you, everyone.
Ma'am, could you please upload the quiz solution?
I have already, oh sorry, I have forgotten to mention. I have already uploaded the answers. It is, it's there. Just wait. So if you go to the files, it's there, like it's not in the class material folder.
Visible, ma'am. Yes, ma'am. Before it was not visible.
Yeah, it's not in that class material folder. It is there outside that folder. So this quiz 1 solution is there. So you can go through this quiz, the solution, and if you find that you are unable to understand something, then we can always discuss.
Yes, ma'am. Thank you, ma'am.
Okay. Thank you. Thank you, everyone.